was a PhD student, my supervisor, this was when Lost was on TV. Do you remember Lost, the TV show? It was like the one that gets stuck on the island. And then I remember the local news agency came to interview my PhD supervisor, who was an early universe cosmologist. I don't know why they picked him of all people, but there was like weird sci-fi stuff happening in that show with time travel, and like they physically move the entire island around the world. And my supervisor is not a very charismatic or like talky head kind of guy. He's very like, let me give you the very detailed derivation of why all of that's nonsense. And so presumably the journalist interviewing him realized this and just needed, like, we need some clips that we can use. So watching the video, there's one bit where the guy is they're talking about time travel and somebody coming back from the dead, and the journalist is like, so would you say that time heals itself? And then my supervisor's like, yeah. And he immediately, like, you could tell he's about to go on and say like, yeah, but no. But they just cut it at, yeah.
Hello everyone, welcome to the Nomads podcast. I'm your co-host Bhavya.
And I'm your co-host Prachi.
Have you ever wondered what the universe was like in its very first moments? Why did matter win over antimatter? What is dark matter made up of? What is dark energy? And could the answers to these questions change the way we understand particle physics itself? Well, in today's episode, we talk to Professor Andrew J. Long of Rice University about all of this fascinating stuff. Andrew is a theoretical physicist working at the intersection of particle physics and cosmology. His research explores some of the biggest open questions in fundamental physics, including early universe cosmology, baryogenesis, dark matter, neutrinos, and of course, physics beyond the standard model. So if you're interested in understanding why the universe exists the way it does, you're in for a treat. So, let's go.
Andrew Long, welcome to the Nomads podcast.
Thank you for having me.
So let us start from the beginning, literally. So when we talk about the Big Bang, most people think of it as an explosion in space. But obviously physicists don't think it like that. So how about you take us through the early moments of the universe?
Right. So our understanding of the cosmological history is informed from principles of general relativity, combined with quantum mechanics and thermodynamics. If you imagine a hot gas, even in a room, as the gas expands, it cools down. And so if we were to run the cosmic clock backward on our universe, the expansion of the universe with time corresponds to cooling down as time goes forward or heating up as time goes backward. So those first fractions of a second after the Big Bang, we're picturing them not as the universe is seen today with stars and gas and galaxies and stuff, but rather a hot soup of primordial plasma in which all of the elementary particles are present, constantly bumping into one another, annihilating and getting produced in pairs. And although we have direct observational evidence for what the universe was doing after it was about 3 minutes old, which is a special time at which the temperature of that plasma was around nuclear energy densities, we really don't have a great handle on what was happening prior to that point in time. And we refer to that epoch in the cosmic history, generally speaking, as the early universe. And a lot of my work is on understanding what might the universe have been doing during those first tiny fractions of a second after the Big Bang. And how did what occurred at that time shape the way in which the universe is today, both in the distribution of structures, in galaxy clusters, as well as the composition of the universe in the form of dark matter and cosmological excess of matter over antimatter and other such things.
Interesting. So again, we can unpack this more. So when we do this thought experiment of running the clock backwards, so up until what time we can run the clock backwards, and when are we confident to say that, okay, from here onwards, we can explain everything? And why can't we explain before that?
So the usual dividing line that people talk about is when the universe is about 3 minutes old. and this is an epoch at which, as I said, the plasma temperature is around nuclear energy densities, and we talk about event occurring at that time known as Big Bang nucleosynthesis.
Mm-hmm.
I see.
And the idea was that the plasma was so hot and dense that particles were scattering. And at that time, the plasma really contained, it's not the same kind of plasma that you would find in a fluorescent light bulb in your office. It's plasma that consists of protons and neutrons and electrons and positrons. And those individual protons and neutrons were scattering in such a way that they actually combined through nuclear fusion to form light elements, lithium and beryllium and so on. And we've been able to observe those light elements present in the universe today through the way that they're present in certain older stars, giving us confidence that our models for the way in which the universe was behaving at 3 minutes old were working out okay. And even beyond that point, as the universe continued to expand and cool down, other events occurred that we can explain in the theories and which match up with the observations. Most notable among them is when the universe was about 300,000 years old.
Okay.
And at that point, the plasma was cooling down so much that electrons, which previously had been, hydrogen atoms had been ionized, with electrons not attached, not forming bound states. But as the plasma cooled down, the electrons and the ions recombined to form neutral atoms. And that phenomenon of recombination led to, there's an associated light that was emitted known as the cosmic microwave background radiation. And, astronomers have discovered that light and now measured it with sub-percent level precision, giving us a wealth of information about what the structure and composition of the universe were back at the 300,000 year mark. So we have a pretty solid handle on what was happening after 3 minutes. But we would love to know much more about what was going on prior to that time, when exciting things may have been occurring relating to the Higgs field or grand unified theories or cosmic strings or quantum gravity.
Interesting. And again, very briefly, what prevents us to look before that?
If you actually would like to look outward and see with light, we're prevented from doing that because the universe was opaque at those times. And so the universe only became transparent to light at that event known as recombination. And we do see the light from that time. And if you'd like to look earlier, we could potentially do that, but we can't do it by using light. Instead, we would need some other probe, like elementary particles known as neutrinos, or these days another exciting topic is the idea of looking into the early universe with gravitational wave radiation.
Right. Interesting. I see. So also during this early universe, it's believed that matter and antimatter should have been produced in equal amounts. And if that were the case, they would have annihilated each other. And we would see no atoms, stars, galaxies, and so on. So what exactly tipped the scale in favor of matter over antimatter, and how do you think about this?
I don't know. I would love to know. You're right that in the lab, we are detecting matter and antimatter, and they appear to have, very similar properties. The electron and its antimatter partner, the positron, have the same mass and the same spin and opposite electric charge, and in many ways they behave similarly. But nevertheless, the universe is made out of electrons and protons and atoms and gas and galaxies and cheeseburgers and that sort of thing. And the universe is more or less devoid of antimatter and anti-gas and anti-cheeseburgers and things. And so we would love to know what occurred, what event transpired in the early universe that led to this excess. And not knowing, we give it a name. We call that problem baryogenesis, so that we can argue about it at conferences over coffee and beers and things. And we know a little bit about baryogenesis, that whatever event took place, it needed to contain a certain set of ingredients, which are known as the Sakharov criteria, which are relating to particles and antiparticles should behave differently because of CP violation, and there should be some way of converting a changing baryon number and these sorts of things. But there are dozens or more ideas about what may have been the baryogenesis event. When in the cosmic history did it actually occur? Which particles and forces were involved? And the jury is still out as to what the physics of baryogenesis was. And it's kind of funny if you think about it. Among all the problems in cosmology, many of them have to do with very ephemeral stuff, like the dark matter and the dark energy, which we don't really touch and feel in laboratories on Earth or in our day-to-day life. They make themselves manifest on cosmological scales, where enormous amalgamations of dark particles help to keep galaxies bound together, so to speak. But the problem of baryogenesis is the problem of us. It's the problem of why are we here in the first place. It is in some ways the most tangible of the cosmological problems, but it's the one that's in many ways the most observationally challenging to access, because although we know that there is more matter than antimatter, and we can even quantify that very precisely. I mean, observations of that cosmic microwave background radiation tell us that there's roughly 1 proton for every 10 to the 10 photons in the universe. So we can quantify exactly how many protons versus antiprotons there are with these types of numbers. But explaining where it all came from is a particularly big challenge and long-standing problem.
I see.
Right. Interesting. So one of the most famous and very strong theories of physics is the Standard Model. It basically describes all the known particles in the universe. So could you talk to us about where exactly does the Standard Model succeed, and what is it that's still missing from the Standard Model?
Right. Yeah, so the Standard Model was developed over the course of the 20th century to describe a variety of different observations coming out of different collider experiments and nuclear physics experiments. And as you say, it captures all the known elementary particles and the forces by which they interact. And it's been wildly successful, more successful than one could have ever imagined at describing the properties and interactions of the known elementary particles. From both energy scales relevant to atoms, even to the highest energy scales that are being probed by the Large Hadron Collider, or astrophysical accelerators that are also accelerating particles to high energies. It's working well across this range of scales. And with the discovery of the Higgs boson in 2012, the last piece of the Standard Model puzzle had fallen into place. And the business of the Large Hadron Collider today is largely about studying what we can learn about the Higgs boson while also working to hopefully discover new particles and tug on some loose threads. But when it comes to cosmology, there's a lot of open questions that the Standard Model fails to address. There's overwhelming evidence that most of the matter in the universe is in the form of some mysterious invisible matter that we call dark matter. And most of the energy of the universe is dominated by an invisible force that we call dark energy that's causing the expansion of the universe to accelerate. And neither of these are described by the Standard Model. What's required is presumably some forces and particles beyond the Standard Model that could hopefully help to fill in the missing pieces of the cosmological puzzle. One of the interesting things about the way in which particle physics and cosmology have developed over the last 30 years or so is that there's been a merging in many ways. That it used to be the domain of the particle physicist to smash particles at high energies, and it used to be the domain of the cosmologist to wonder about if the universe is going to bang or crunch. But as cosmology has been bringing up cosmological observations have been unveiling new problems, like the problem of dark matter and the problem of dark energy. It's fallen on particle physics community to try to provide explanations for those mysteries. So there's been these days, there are no longer so many particle physics conferences or cosmology conferences. There's usually particle cosmology conferences getting together.
So again, coming back to baryogenesis and CP violation. So are there ingredients in the Standard Model that would perhaps explain this matter-antimatter asymmetry? And what are some of the hints that are available now that you're saying that particle physicists are participating more and more in these cosmological studies?
Yeah, so coming back to the Sakharov criteria, there are 3 conditions that should be met in order to successfully explain why there's more matter than antimatter. One of these is that there should be a process that violates baryon number. Baryon number is the charge that counts a plus a third for all the quarks or things made from quarks, negative a third for all the antiquarks or things made from antiquarks, and zero for everybody else. So, for example, if you could convert an antiproton into a proton, you would be changing baryon number by +2 units.
Right.
And the Standard Model actually already contains a process that violates baryon number, thanks to the electroweak force. And this process is sometimes called the electroweak sphaleron. Sphaleros is, I believe it's Greek for ready to fall. It was so named because of the way in which it's a saddle point solution of the field equations.
Okay.
It's like being at the top of a hill. And the electroweak sphaleron features prominently in many models of baryogenesis, because it's already a part of the Standard Model. One need not even add in that extra ingredient beyond what's already given to us from the Standard Model. You can't avoid having it. So the Standard Model helps in that regard. It's kind of tantalizingly giving us one of the necessary ingredients for baryogenesis. One of the other ingredients is CP violation. So this means that the forces that are playing some role in particles and antiparticles that interact at different rates. And again, the Standard Model accommodates CP violation. It's already been observed in the quark sector through the delta CKM phase of the so-called CKM matrix. And there are experiments searching for evidence of CP violation in the neutrinos as well, like the Dune experiment, by making observations of neutrino flavor oscillations. But the amount of CP violation that's present in the CKM matrix is too small to explain the origin of the matter-antimatter asymmetry. And so it's generally believed that additional sources of CP violation are required in order to achieve baryogenesis. In other words, you have to have new forces that behave differently with regard to particles and antiparticles in order to successfully explain the matter-antimatter asymmetry. So it's kind of a funny spot that the Standard Model puts us in, where it's giving us a little bit of what we need, but not everything that we need.
Right.
And it calls for the presence of new physics.
Okay, beyond the Standard Model.
Beyond the Standard Model,
Yeah. So you briefly mentioned the Dune experiment. Could you talk more about what exactly is the purpose of the Dune experiment?
Right. So this is not really my expertise, but there's an experiment known as Dune that's currently one of the biggest particle physics experiments operating in the U.S., which involves studying the physics of neutrino flavor oscillations, where the three different flavors of neutrinos, electron type, muon type, and tau type, can transform one into another. This was first observed through something called the solar neutrino anomaly, in which neutrinos produced in the sun and detected here on Earth were found to exhibit this kind of flavor oscillation phenomenon. And now a variety of experiments around the world are trying to probe it in a laboratory, where you would make neutrinos with one flavor in one laboratory and let the neutrinos travel some distance and detect them in another laboratory, maybe across the country, maybe in another building in the same campus, maybe in another laboratory in a different part of the country, maybe in a different country, in order to study the way in which neutrinos transform from one flavor into another. The Dune experiment uses a beam of neutrinos created at Fermilab, the National Accelerator Laboratory outside of Chicago, and detects them. I forget exactly. Let's just say 1,000 kilometers away. Don't quote me on that. Detects them some distance away to observe the way in which the neutrinos would experience flavor oscillations at really large distance scales on the order of 1,000 kilometers. And by doing so, they hope to measure a couple of things. One of the things has to do with the mass of the neutrinos, whether they're two light guys and a heavier guy, or one light guy and two heavy guys, so that whether they're so-called normal ordering or inverted ordering. And something else that they're trying to measure, as I said, was whether neutrinos and antineutrinos would oscillate slightly differently. And so hopefully the Dune experiment will begin taking data and reporting on their measurements in the 2030s. And we'll begin to finally unravel the remaining mysteries about the physics of neutrino flavor oscillations.
Right. And we've been talking about, and you mentioned how if we want to look before the 3 minutes, neutrinos are a way to probe it, and we cannot use light. What makes neutrinos so special?
Yeah, so neutrinos, among all the elementary particles that we know of in the Standard Model, the neutrinos have the weakest interactions, which is to say, the charged particles like the protons or their constituent quarks or the electron or its partner, the positron, interact with the photon, the electromagnetic field. And this is what's responsible for like holding me here in my chair rather than letting me slip into the ground, falling towards the center of the Earth. It's the electromagnetic force that we interact with on a daily basis when we bump into things, or when our eyes let us see things. And there are some particles that are electrically neutral, like the neutron or the neutrino, and that neutrino in particular only interacts through the so-called weak force, which means that if a neutrino is produced, say, on the surface of the Earth due to a beta decay in a nuclear reaction, that neutrino could zip off into space through the atmosphere, but it might even zip off into the Earth, passing into the dirt. And so the neutrinos have enormous ability to penetrate through ordinary matter. And if we ask about the conditions of the first fractions of a second after the Big Bang, when the universe was filled with this hot plasma, the plasma was opaque to light and ordinary, the particles of light, the photon, but the early universe would have been transparent, at least at some point, to these neutrinos. And so by observing the neutrinos, we get to glimpse backward into a period a little bit earlier than when the light itself was emitted. And people refer to this as the Holy Grail. Excuse me. Whether or not we could actually detect the neutrinos that were created and traveling to us from the Big Bang, people have referred to that as the Holy Grail of neutrino physics. We've never detected those neutrinos in a laboratory. We've only ever detected their influence on the cosmic microwave background radiation. But if we could detect those neutrinos in a laboratory, the so-called cosmic neutrino background, it would provide us with a wealth of information. We'd be basically pushing our knowledge about the cosmic history backward from the recombination epoch to the neutrino decoupling epoch.
Right.
And how would we know that, hey, this neutrino is from that epoch? How would we know that?
Yeah, so the neutrinos are also notoriously light particles. They're the lightest known elementary particles, having masses of about like a tenth of an electron volt. And for reference, the electron's mass is 500,000 electron volts. So these are very, very low mass particles, which means that when they're created in nuclear reactions, like in the sun, they're produced with an enormous momentum. So they're very relativistic. They're traveling at nearly the speed of light.
Right.
But the neutrinos that were produced at the Big Bang, the cosmic neutrino background, were also produced relativistic, but they were produced very, very long ago. And in the meantime, the universe has been expanding for about 14 billion years.
Right.
And it turns out that if you take a massless, or you take the cosmological expansion leads to a phenomenon known as red shifting, in which the momentum decreases as the in a manner of speaking, the de Broglie wave is stretched out. And so the relic neutrino background today would be non-relativistic. In fact, these would be presumably the only source of non-relativistic neutrinos in the universe, because every other reaction that creates neutrinos is creating relativistic neutrinos. And so the way in which you could search for them would be, for example, the following. You take a beta decaying isotope like tritium, which is to say that tritium is an isotope of hydrogen with two neutrons and one proton. And it experiences a beta decay where one of the neutrons converts into a proton, giving you helium-3, and it ejects an electron, and it ejects an electron-type antineutrino. And so you can measure the spectrum of the electrons coming out of the tritium. And there's a whole lot of low-energy electrons, and then as you look at the spectrum at higher and higher energies, eventually there's some end point in the beta decay spectrum above which you can't have any more energetic electrons. The Q value for the reaction is like 18.6 keV or so. But you don't get to see the neutrinos, because the neutrinos, as we discussed, are very, very weakly interacting. So the neutrino will just zip out of the room and out of your lab, and it's lost, but you're measuring the electrons. Yeah. On the other hand, imagine that you have some neutrinos that are incident onto the tritium from space, these relic neutrinos. And those neutrinos can get captured by the tritium and trigger a beta decay. And now that electron is coming out with not just the kinetic energy it inherits from the Q value of the reaction, but it also carries away, it also comes out with the energy that the neutrino brought in, the rest energy of that neutrino, an extra mc squared.
Right.
And so if you look at the spectrum, what you'd expect to see is a beta decay spectrum with some endpoint, and then a small gap, and then beyond the endpoint, on the order separated by a neutrino mass or two, there would be a little blip. And the little blip would correspond to the relic neutrinos that had been captured and gave the electron a little bit of extra energy.
Interesting.
Yeah, so you could try and look for it's one of the primary strategies that have been explored for searching for relic neutrinos.
And in the spectrum, we would see like this shift would be something like from a particle that had non-relativistic energy, and that's what would be the signature.
Right.
Interesting.
Yeah, if the neutrinos had been relativistic, they would have been bringing in more energy, and so the electron would have been even further beyond the endpoint.
Right.
But the closest the electron could be to the endpoint would be set by the rest energy of the neutrino, which is just its mass scale.
I see.
So
Interesting.
The
Very
blip
cool.
is really, really, really close to the endpoint. And in fact, that's one of the reasons why these types of measurements are exceptionally challenging, and that's why the neutrino experimentalists would refer to this as the holy grail of neutrino physics.
I see. Yeah. So let's talk about dark matter now. The first question that anyone thinks about dark matter is we can't see that, right? So how do you know it's even there?
Right. Yeah, it's astonishing that we have an abundance of evidence for the presence of dark matter in the universe, and all of it has to do with the fact that dark matter pulls on things. And astronomers and astrophysicists have been watching dark matter pull on things in a variety of different astrophysical systems and at different epochs in the cosmic history. So the first evidence for dark matter was identified by Fritz Zwicky in the 1930s, and he was looking at the motion of galaxies in a group known as the Coma cluster, which is a cluster of galaxies. And he was able to make measurements of the speeds of the different galaxies in the cluster, and he noted that the galaxies appeared to be moving more quickly than one would have expected based on the fact that they were pulling on one another gravitationally. Like, of course, the planets go around the sun thanks to the fact that the sun exerts a gravitational force on them. And if the sun were to pull harder, they would move faster. And so similarly, by looking at the speeds of the galaxies in the Coma cluster, one can infer the mass of the Coma cluster. And what Zwicky identified was that there was extra mass in the Coma cluster beyond what could be associated to just the stuff that was glowing. And he's the one who coined the phrase dark matter.
I see.
And in the years since then, evidence for dark matter has been cropping up in dozens of different places. So the work of Vera Rubin in the 70s identified dark matter by she was surveying different individual galaxies and looking at the motion of the stars in the galaxies. But similarly, roughly speaking, she was finding that there was the stars are moving more quickly in those galaxies than you could associate to just the luminous mass alone, that there needed to be a dark mass in the galaxy to provide the additional gravitational force that explained the speed. So maybe I should say the astrophysical observations of the Coma cluster and rotation curves of galaxies leave open alternative theories for what might be going on, that perhaps the dark matter is not a new kind of substance, but it's a reflection of the fact that we've misunderstood how gravity works. But a much more definitive test of the dark matter comes from precision observations of the cosmic microwave background radiation, in which not only do we get to detect this 2.7 Kelvin glow across the sky, which is this photons that were created during the recombination event when the universe was 300,000 years old, and they've been traveling towards us till today. But we also get to measure with percent level precision how the intensity of that radiation varies across the sky, how the temperature changes as you move across the sky. And there's a theory for describing why the temperature would vary in that way, which takes as an input dark matter. And things are working out beautifully, that the data is perfectly consistent with the dark matter making up 5 times more matter, making up about 20% of the cosmological energy budget.
This is lambda CDM.
Yeah, this is lambda CDM.
Right. Yeah. So the only thing common between ordinary matter and dark matter is that they both interact with gravity. Is that the only common thing between them?
All of the evidence that we have for the presence of dark matter derives from the fact that it interacts with gravity. And it seems to be interacting with gravity in the same way that ordinary things interact with gravity. Beyond that, all we know about dark matter is what it does not do. So we know that if it carries electric charge, it does not carry as much electric charge as an electron or a proton. We know that if it decays, it does not decay very quickly because it survives for the 14 billion year history of the universe. If it's an elementary part, if it's a composite object, it could be an elementary particle, like an electron. It could be a composite particle, like a proton or a neutron. It could be a composite macroscopic object, like a black hole or a quark nugget, with a mass that you would measure in kilograms rather than measuring in electron volts. So that the space of things that we don't know about dark matter is vast.
Right. And are these one of the reasons that neutrinos were considered as a dark matter candidate?
Right. So neutrinos seem to be fitting the bill. Like they're a particle that we know exists. So we don't have to hypothesize the existence of new particles and forces. They're electrically neutral. And we know that we believe that they were present in the early universe. They were part of that primordial plasma. And as the plasma cooled, they would have decoupled from the plasma and began traveling to us today. In the same way that the cosmic microwave background radiation, those photons decoupled from the plasma have been traveling to us today. But the problem is that the neutrino mass is inferred from these observations of neutrino flavor oscillations with a variety of different experiments on Earth and astrophysical neutrinos from the sun and produced in the atmosphere. And from that, we know that the neutrino mass scale is measured in, we don't know exactly what it is, but it's measured in tens or hundreds of tenths or a tenth of an electron volt. It's measured in tenths of electron volt. And so that means that they wouldn't provide good candidates for dark matter. The problem is that they would be so light that they wouldn't have clumped together quickly enough to allow for the universe to have the galaxy halos and structures that we see today. People refer to neutrinos as an example of hot dark matter or warm dark matter, whereas really what we're looking for is cold dark matter, meaning that the particles are sufficiently low velocity dispersion that they can more easily form clumps and thereby build up to form the overdensities that host the galaxies and the galaxy clusters that we observe.
So what are some of the other dark matter candidates and what makes them unique, and why are axions suddenly back?
So let me start by saying that, let me first mention the thing I studied. So you might say, since the dark matter is only known to interact gravitationally, is it possible to have a theory for dark matter where it's a new kind of elementary particle that only interacts through gravity? It doesn't interact with any of the other fundamental forces or any other not yet discovered forces. And of course, if that's your hypothesis, it perfectly well accommodates the data. The data would love it if the dark matter only interacts through gravity, because that's all the evidence that we have anyway. The experimentalists would hate it because they're not going to be able to actually detect things in a laboratory through gravitational interactions alone.
Right.
But nevertheless, it's an interesting theoretical exercise of, can I explain the dark matter using only gravitational interactions?
Right.
And the real question then is not so much explaining the phenomena that dark matter induces with regard to rotation curves and things. It's about explaining, where did the dark matter come from in the first place?
Right.
How do you make dark matter using gravity? And a lot of my work over the last several years has been investigating a phenomenon that we call cosmological gravitational particle production, in which it's gravitational interactions alone that are responsible for creating dark matter. And it's kind of an interesting phenomenon where the expansion of, it's been known since the work of Parker in the 60s that the expansion of space itself can lead to creation of particles. And if you imagine the earliest fractions of a second after the Big Bang, during a period known as cosmological inflation, the universe was expanding the fastest. And that's the time when particle creation would have been most effective. And so it turns out it is possible to explain how the dark matter may have arisen, even if it were only interacting through gravity, thanks to the rapid expansion of the universe during cosmological inflation. But more bread and butter examples of dark matter fall into two categories. One of them, which you mentioned, is the axion, and the other is the WIMP. So the WIMP is an acronym standing for weakly interacting massive particle, and depending on who you ask, the weak there can mean different things. There was some point at which weak there referred to the standard model weak force, but now it kind of refers to weak forces more generally. People try to distinguish WIMP with a capital W or a little w for the ones that interact through the standard model weak force or a more generic type of not so strong force.
Right.
And the WIMP is an exceptionally compelling idea. It's the idea that the dark matter does have interactions beyond gravity that allow it to scatter with and annihilate into standard model particles. And those interactions may have been occurring rapidly in that hot fireball in the early universe, such that the WIMP and the ordinary particles were in thermal equilibrium in a plasma. And again, as the universe expands, it cools, the plasma contained within it cools down, and eventually the plasma would have become too cold for the WIMP to maintain thermal equilibrium, and it would have decoupled, meaning that you just have some diffuse gas of WIMP particles now floating through space. They no longer, they're still a plasma, but the WIMP particles interact so weakly they don't bump into the plasma, and they more importantly, they don't annihilate with one another into the plasma, nor does the plasma particles annihilate, producing pairs of WIMPs. So we call that decoupling. And we already know that that's what happens with the neutrinos. The neutrinos maintained thermal equilibrium, and then they decoupled when the plasma got too cool. So it's not that hard to imagine that maybe there's new hypothetical particles, new dark particles, that would have done something similar. And the WIMP idea received a lot of attention in part because it's easy to find candidates for WIMPs in some of our favorite theories of elementary particle physics. Like if you take the standard model and add a concept of supersymmetry, that requires each of the known elementary particles to have a partner. And we like that idea for various reasons associated with the Higgs boson, and we like it for its testability at colliders. But in addition, the new particles, some of them are WIMPs in the sense that they would have maintained they would have been electrically neutral, they would have been weakly interacting, they would have maintained thermal contact in the early universe, and their decoupling would have led to the creation of a gas of these particles floating around in space today that could have clumped up and explained dark matter. So the WIMP was and remains to be now an exceptionally theoretically compelling and highly testable paradigm. And thanks to it being highly testable, we've really pushed it to its extremes, and by doing so, falsified certain incarnations of the WIMP. There are experiments in the U.S. and around the world that are trying to detect WIMP dark matter, using, for example, big multi-ton vats of liquid xenon, where the idea is that a WIMP would enter the big vat of liquid xenon, and if you get lucky, it would bump into one of the xenon nuclei, jiggling it just hard enough such that it would maybe ionize that atom a little bit, or emit some light. And you'd be able to detect the ionization, you'd be able to detect the light. And by doing so, if you have an understanding of what the backgrounds are in those experiments, and you can say with confidence that a certain event was not a consequence of the background, then you would be able to claim to have detected a WIMP in that way. And those experiments have been under underway for decades in various incarnations, scaling up, getting bigger and more sensitive, and they've been very powerful in falsifying certain incarnations of the WIMP. So we now know things about like what parameter space in terms of mass and coupling are not allowed, and they're finally pushing the WIMP into a corner where the next iteration of these experiments would hopefully discover a WIMP or possibly close a window there. But as the WIMP program is progressing into its advanced stages, and evidence has not yet arisen for the WIMP dark matter in these types of experiments, the community has cast attention on what many would consider to be the second best, or maybe in some people would consider to be the very best candidate for dark matter, which is the axion. And the axion is also an old idea in which it was initially proposed to try to solve a problem in the elementary particle physics that has nothing to do with dark matter. It has to do with the strong force, which is responsible for holding together the nuclei, the protons and neutrons. And it had to do with explaining why the electric dipole moment of the neutron is so tiny, whereas it could have potentially been much larger. But various experiments have attempted to measure the neutron's EDM and never succeeded, but only placing upper limits on its size, saying it's compatible with zero. They've succeeded at constraining it to be very tightly close to zero. And the axion was proposed to try to, there was a proposed solution to that problem known as the Peccei-Quinn solution, named after Roberto Peccei and Helen Quinn. And the axion is a byproduct of that solution. It's a new hypothetical elementary particle that would be necessarily interacting with ordinary matter because it's related to a problem about the nucleons after all. And typically it would be a very light particle with masses measured in maybe microelectron volts. And so that idea has been around for 45 years or so, and people have been searching for axions in laboratories as well. In the US, the real flagship experiment is known as ADMX, where they're trying to use resonant cavities to detect axion particles as they're passing through the lab by converting them into photons, because axions are expected to experience this phenomenon known as the Primakov effect, where an axion exposed to a magnetic field converts into a photon. And so, but as the community has been considering alternatives to the classic WIMP paradigm, there's been an explosion of interest in axions over the last decade or plus. Part of that has been on the experiment side, where new proposals have been put forward to detect axions across different mass ranges, which ADMX is unable to access. And a lot of it has been theory work, some of which I've been engaged with, where we've been looking for axions or its cousin axion-like particles, which are expected to impact different cosmological and astrophysical observables as well.
Super interesting.
Right. So if gravity is the only evidence, like not the evidence, but if we know for certainty with that dark matter interacts with gravity, I would assume that gravitational wave astronomy must help, like provide some insights into this. Is that true?
Yeah. So there's different ways in which dark matter's gravitational influence could be felt in astronomical observations. So maybe a simpler thing than gravitational waves is just asking about if I have a blob of dark matter somewhere in space, because that blob of, and by blob I mean like a big spherical ball, which you could imagine it's hosting a cluster of galaxies, which then has their own denser balls contained within. But there's some light behind that, because, for example, the cosmic microwave background radiation is, when it travels to us and telescopes on Earth, it has to pass through the whole universe.
Right. Yes.
So it's passing. And some of it passes by these clusters of galaxies. But Einstein taught us that light is deflected by mass. And so the big massive ball of dark matter, that halo, would deflect the light of the cosmic background radiation. And this phenomenon is known as gravitational lensing. And in particular, in this context, it's called weak lensing because the deflection is very subtle.
Right.
It's not weak because of WIMPs or in any way. It's just weak because it's subtle. And so that's something that has been observed already with precision observations of the cosmic microwave background radiation, the subtle deformations of the pattern of bright and dim or hot and cold spots across the CMB due to the foreground structure. So that's what I was referring to by there's a variety of different observational handles that we have for the nature of dark matter. But another is maybe more relevant to gravitational waves is there's a exciting idea that perhaps the dark matter itself is some massive objects like black holes. In fact, when the LIGO experiment reported their detection of the gravitational waves from binary black hole mergers in 2015, they reported that they had detected, I think it was maybe a 30 solar mass and a 50 solar mass black hole merging to form a, I don't remember, let's say 70 solar mass black hole. And soon afterwards, that was very exciting. And that really transformed the way that we think about the cosmos and what we can learn by peering out into it. But in regard to, and that has nothing in and of itself to do with dark matter, it would seem. It just says that big black holes in some distant galaxy happen to meet and merge, emitting some enormously strong blast of gravitational waves, and so strong that even after traveling to our galaxy very, very far away, the gravitations were still strong enough to be detected by this extremely precise experiment. But you could ask whether or not the black holes that LIGO detected are the remnants of collapsed stars that would have gone through their life cycle and then gone supernova and leaving behind black holes, or whether those black holes are, in fact, relics of the early universe, that maybe they formed also in the first fractions of a second after the Big Bang and just happened to hang around in the universe all this time, and that is the dark matter.
So are these called primordial black holes? I see.
Yeah, so this refers that people refer to this idea as primordial black holes of black holes that were created not through the collapse of stars, but through physics in the early universe, typically imagining big overdensities that themselves just collapse. It was originally Hawking's idea.
Very interesting.
And so the primordial black holes, that the discovery of binary black hole mergers through their associated gravitational wave radiation by the LIGO experiment sparked an enormous amount of activity in the study of primordial black holes and their connections to dark matter. And so in the years since then, we've come to understand that the black holes that LIGO is observing at tens of solar masses are very unlikely to be primordial black holes. Because if such large black holes were present during the epoch of recombination when the cosmic background radiation was released, it would have led to an imprint on the CMB.
I see.
Basically, the big black holes would have accreted the plasma, heating it up, and that heating would have led to would have been reflected in the temperature patterns of the CMB. But nevertheless, there's still space for the dark matter to be black holes. As long as the mass of those black holes are down at around asteroid masses. And people are working very hard to try and test that so-called asteroid mass window and finally settle this question of whether all the dark matter can be black holes. Or even if all the dark matter couldn't be black holes, one can imagine that some subfraction of the dark matter is made up of black holes. Maybe 1/1000th of the dark matter is black holes, and the other 99.9% are axions.
Interesting. So trying to sort of circle this back. So we know that the universe is expanding, also attributed to dark energy. We discussed about dark matter candidates. Also gravitationally produced particles during the time of inflation. So do you think, I mean, just being very ambitious, do you think that there's like a dynamical explanation and all of this sort of fits into the baryogenesis problem? And is it something that you're thinking about? So for example, inflation was a dynamical process to settle the flatness problem, the temperature distributions, and so on. So
I mean, the holy grail for me would be one theory that explains it all.
Okay.
It slices, it dices, it explains the dark matter, it explains the baryons, it explains the current accelerated expansion of the universe, which we call dark energy. It explains the early accelerated expansion of the universe that we call inflation. And people have put forward paradigms that try to fit all the pieces together into one, framework using kind of unification and minimalism as guiding principles. And I think I've even worked a bit myself on like models of inflation that give way to there's theories called quintessential inflation, where it's the same field, the so-called inflaton field, that was responsible for both the early accelerated expansion of inflation and the late accelerated expansion of dark energy. In some ways, I feel like it's asking for too much. I think the universe, as humans, we like the idea that it will be minimal and unified and everything will fit into one nice package. But I think we have no guarantees that nature will be so kind to us as to allow, as if everything had been designed to fit together just so. Like, for example, in the standard model, there's extraneous stuff in there. Do we really need the tau lepton? Do we really need this top quark? I mean, there's things that aren't, needed as part of for the consistency of the theory, but they're needed because that's what the data tells us the way the universe works.
of course, yeah.
And perhaps it's the case that we just haven't come to understand yet the unifying principle of why those things are needed, and people are investigating those ideas as well. But I think it would be a perfectly acceptable attitude to imagine that the universe is just what we got, and there may not be a neat way of fitting it all together. There should be one description for everything that may have many, many different knobs and buttons and things on it.
I see.
But one thing I will add, though, that is a tantalizing clue is about the dark matter and the regular matter. So it turns out that there's about 5 times more dark matter in the universe than ordinary matter. And that's very peculiar, because if you imagine the mechanisms that create dark matter, there's usually a knob somewhere in those theories, meaning a parameter that you can dial within some allowed range. And it would allow for maybe much more dark matter or allow for much less dark matter, but it turns out to, and similarly in the theories that explain the cosmological excess of matter over antimatter, so-called baryogenesis, there's some other knob or a couple of knobs.
Right.
And they would allow for much more baryon asymmetry, maybe much less baryon asymmetry. But somehow it seems like these two seemingly independent phenomena of creating the dark matter and creating the matter-antimatter asymmetry have somehow lined up to differ only by a factor of 5. And
So it's like a fine-tuned number in some sense.
Right, yeah. So it seems to be somehow set just so. And even though the physics, as far as we understand, the physics that generated the two were independent of one another. But it motivates one to think about paradigms in which both the dark matter and the baryonic matter are being created together through some one unified principle. And I think that's a very interesting question.
And so the recent results about dark energy or the expansion varying over time, would that have any consequences? And
yeah, so there's recent measurements by the DESI collaboration, which is a galaxy survey where their job is to point a telescope out into space and find galaxies and try to locate them. It's easy to figure out where they are on the sky, and they try to figure out where they are in 3D space by getting a distance to them. And if we had a map of where all the galaxies were, we're not just seeing where the galaxies are today, because it took a very long time for the light to travel to us from those distant galaxies. So as we look at further and further galaxies, we're looking back in time. So actually, by mapping out where all the galaxies are, we're mapping out how the universe has evolved in its later stages, in its more recently. And so you can learn about things like the dark energy, which is which is indicating that not only is the universe expanding today, but that expansion is accelerated. And that what the DESI collaboration has identified is evidence that the expansion may not be a constant acceleration due to dark energy, but rather an evolving dark energy.
Right.
And I guess this relatively recent recent, I don't want to use the word discovery. It's relatively recent evidence that they've uncovered that is getting a lot of attention, and people are investigating on the theory side what kinds of physics could be responsible for the evolution of the dark energy, paradigms like quintessence that have been around for a long time, long before these measurements were made. And people are asking questions about how one can make other observations to confirm or refute what DESI is seeing. But if the dark energy were evolving, then it fits quite naturally into these paradigms like quintessential inflation, where there's some field throughout the universe that is maybe slowly falling down a hill,
Right.
and rolling down a potential, and that that evolution of the field is reflected in the evolution of the dark energy, and then imprinted on the distribution of the galaxies that DESI observes.
I see. Right.
People often try to associate dark, but as for your question about putting the pieces together, I think it's people will more often try to connect dark matter and dark energy because they both got the word dark in them. And I feel like this is a mischaracterization of what the physics is based on the language. And I think obviously if you call two things dark, and it's the natural question is going to be, are they somehow related to one underlying principle? But we really ought to have called it, say, invisible matter and just like acceleration energy.
Yeah.
And forget about the words dark. I guess we can blame Fritz Vicky for that one.
Physicists have been very bad with naming things, I mean, throughout.
That's true.
Yeah.
So I think as for trying to find theories that tie together the dark matter and dark energy, I don't know if there's necessarily a connection there, as opposed to what I was saying a minute ago about tying together the dark matter and the baryonic matter. The fact that they both seem to be similar to one another in abundance is
exactly.
a big clue.
Right.
I think it's a clue that something's going on.
All right, we're past the hump. Moving to the tail end of the podcast. We would love to know what your journey as a physicist has been like. How were you introduced to physics as a child, and some highlights of your journey up until being a professor at Rice?
Sure. I think I was always into science when I was a kid. I mean, way back in elementary school, I remember getting really into biology, and then taking chemistry. I got really into chemistry. But then finally, I think it was junior or senior year of high school, studying physics, I realized that I only liked chemistry because it looked like physics.
Fair enough, yeah.
And similarly, my mom was always into space. I mean, she was of the generation to watch Carl Sagan. I think her and her generation
Cosmos,
through the Cosmos series, and they really fell in love with the science of space. And so she bought me a telescope when I was a kid, and we were out in the backyard staring up at the stars in Delaware, where I grew up. And I think I inherited a lot of that love for science and space and physics from my mom. Of course, my mom never did any physics. She herself didn't have a college education. But she was very supportive of me and my sister. So we were raised, she was a single mother, so we were raised just by our mom. And she really provided a lot of opportunities for us to succeed and excel. And so she really pushed me to perform well in school. She encouraged me to apply to Cornell, where I ended up doing my undergrad, getting some amount of financial aid to go there because it's not cheap. And where I knew that I wanted to study physics even on day one. And it was a lot of fun and a lot of work studying physics at Cornell. I remember on the graduation ceremony for the department senior year, when somebody, I can't remember who it was, got up to speak to the group of the new graduates saying, well, congratulations on getting your degrees. As you probably know, the physics major has the highest credit hour requirement of any degree on campus. I'm like, I did not know that, but it makes a lot of sense now of why I was in the library until 2 a.m. every night until they would kick us out of the library, and I would go back to the dorm to study when all of my friends were out having a fun time or just sleeping like ordinary people. So I was able, while I was an undergraduate physics major, not only to take a lot of classes as part of the undergraduate curriculum, but even take some graduate level classes in particle physics and cosmology, which really whet my appetite for those more advanced topics. And I did research with the accelerator laboratory there and a summer internship program. So then when I was applying to PhD programs, I knew that I wanted to study particle physics and cosmology or something in that area. And I was very fortunate to be admitted to the University of Wisconsin, where I did my PhD work with Daniel Chung, who's known for different studies of early universe cosmology, baryogenesis, dark matter, cosmological observables, and so on. And so PhD was also quite challenging. As you guys would know, you're doing your PhDs now. It can be a lot of work and a lot of stress, but in the end, I hope you'll agree with me that it can be very fulfilling.
Definitely.
And I ended up getting my degree in 2012, which was excellent timing because the work that I was doing was on the physics of the Higgs boson and its role in cosmology. And as you know, the Higgs boson was discovered in 2012.
Perfect. Yeah.
So the first couple of my papers, you would see, if you pull them up, you'll find plots where we're varying the Higgs mass, which was unknown at that time because it hadn't yet been discovered, from 114, which was the LEP limit, up to maybe 150 or something. And by my last paper, we were just setting the number to 125 GeV, which was the observed Higgs boson mass. And there were a lot of exciting questions both then, and they persist even now, about what role did the Higgs boson play in the cosmic history in that hot, dense plasma state that perhaps it's where the matter-antimatter center was formed. And I went on to do a couple of postdoctoral studies at Arizona State University and University of Chicago, and 1 year at the Line Weber Center at University of Michigan before coming down here to Rice 7 years ago. And it's been wonderful working here at Rice and getting to share with my students the same kinds of excitement for physics and convey to them some of my perspective on the way in which physics should be done.
Sure. If you could give some advice to a younger you who just started his journey in physics, what would it be?
I guess don't forget to sleep. I think I learned too late in life that sleeping is an important part of learning as well. And I don't know.
Is there any advice you give your students who join your group as a PhD student?
I think something that students and I guess this was also true of me as a student, that students struggle to appreciate, especially in the PhD program, is that if you think about life in school, from kindergarten up until college, your interactions with school are usually you go to a class, the instructor gives you an assignment and tells you, bring it back in a week. And there's some implicit assumptions there, like you will be able to complete the assignment, and you will be able to complete it in a week. Because if the assignment could not be completed or it couldn't be completed in a week, the instructor would be a real asshole because giving you such a thing. Whereas, of course, in research, we're asking open-ended questions.
Right.
We're setting timelines for ourselves that I think I can get this done in a month, or I think I can get this done in 6 months. But you often find that the question you set out that you thought would take a month takes a year, or the question you thought would take 6 months can never be solved. It's too much. You want to try to ask those big questions so that you're doing novel, impactful work. But you also need to be conscious of the fact that you won't know unless you're working hard through a sustained effort whether or not the payoff is going to be worth it. And I think this is something that I've found PhD students come to realize at some point, maybe in their second, maybe in their third year of the degree, as they start to take greater ownership of the work that they're doing. And perhaps I would have gone back, and nobody ever really explained this to me. I just learned it organically, which I think is the way in which many faculty you'll find, professional researchers you'll find, stumbled into this fact. But I think if somebody had set me down on day one and just kind of laid out how research and study differ, and how to approach research versus how to approach study, that would have had an impression on me back then.
Right.
Wow.
Right. Do you think that academia has changed over all of these years when you were in grad school and now you see your own students?
There's definitely ways in which academia is changing with technology. And I mean, this is probably not what you're asking about, but I mean, the ability to ask Claude or ChatGPT or an AI, I want to do this calculation. Can you lay out the ingredients for me, or can you tell me if somebody's already done it, or can you propose other ways of thinking about this? Changes the mode of working, even for theoretical physicists like me, or for coding activities where it's like I need to write a code that solves for nucleosynthesis BBN chains. Can you give me the code and get you started? And it's definitely impacting the way in which the faculty instructors are interacting with the undergraduate students and the graduate students for examinations and things as well. But there are some things that I feel persist across time, where the developing the skills of being a good researcher really requires some amount of giving yourself the space to think, taking a walk from time to time to clear your head and let the ideas simmer, taking notes on the things that you're hearing about in seminars and lectures, and then looking at the notes later and letting those ideas jumble around in your brain and trying to put them together in new ways and see if you're coming up with new solutions to problems that have been outstanding for 50 years or more. I think these kinds of activities are something that creative researchers excel at, and I don't know if it's something that AI will ever replace.
Interesting, yeah.
But maybe it will replace me, I don't know.
Well, thanks, Andrew, for doing
my
this.
pleasure.
Thanks for being on the
a lot of
Nomads
fun.
podcast. We had so much fun. Thank you.
Thank you for having me.
Yeah.
Of course. Thank you.
Thank you very much.